Alright, in this video we'll be talking about resonance in AC circuits. So obviously the key idea here is the idea of resonance. So resonance occurs when a system is driven at exactly the right frequency, causing a maximum response. Okay, so the last time that we saw resonance in NCEA level 3 was when we were looking at the idea of simple harmonic motion, okay, and we were adding energy at the natural frequency of the simple harmonic motion system. And so if we look back at that situation, when we were driving that system, aka when we were adding energy at the system, at exactly the right frequency, aka the natural frequency, the amplitude continued to increase up until we got a maximum response, aka our amplitude was at a maximum. Okay? And so a very, very similar thing happens in AC circuits. In AC circuits, we want to tune the frequency of the AC power supply, so the frequency of the AC power supply, such that we get a maximum current, okay? So the current being maximum is our maximum response. And so now I want to introduce you to LCR circuits, okay? This is where we have an inductor, a capacitor, and a resistor within an AC circuit, okay? So we have our AC power supply. Therefore, we're going to have an inductor, a capacitor, and a resistor all in series, like so. So as you can see, we have LCR. And so if we draw the voltage phase diagram for this circuit, we're going to have the voltage of our resistor coming to the right like so. And as we know, the current in this circuit is going to be in phase with the voltage across the resistor, okay? We already know that the voltage of our capacitor lags the voltage of our resistor by 90 degrees, okay? And the voltage of our inductor leads the voltage of our resistor by 90 degrees, okay? And so as you can see here, depending on if the voltage of our inductor or the voltage of our capacitor is larger, depending on which one is larger, either the voltage of our supply is going to lead the current or the voltage of the supply is going to lag the current, okay? So obviously, we're going to have the situation where the voltage leads the current when the voltage across our inductor is larger than the voltage of our capacitor, alright? Because this vector line right here is equal to VL minus VC, okay? And a very, very similar thing, when our supply voltage lags the current, this vector here is still equal to VL minus VC, okay? And so therefore, if VC is larger than VL, we're going to get a negative value, and so that just means that our vector is pointing downwards, alright? So that is the phasor diagram for an LCR circuit. And so just like our other phase diagrams, we can apply Ohm's law to this phasor diagram, and because we know that current is the same at all positions throughout the circuit, if we remove current from our phasor diagram, we can get our phasor diagram in terms of our impedance, our reactance, and our resistance values, okay? And because the current is the same at all points, the shape of our phasor diagram is retained, okay, and so all the geometry remains the same. And so therefore, we're going to have our resistor over here, the reactance of our inductor up here, and the reactance of our capacitor down here. And again, our total impedance is going to be the vector addition of all this, alright? So now, going back to our definition of resonance, in an AC circuit, we said that resonance is achieved when our current is at a maximum. And as we know, Ohm's law is V is equal to IZ, right, where our Z is our total impedance. And so if our voltage value is fixed, in order to maximize our current, we must minimize our impedance value, okay? And also, if we look at our definition of resonance, it's about tuning the right frequency, okay? As we know, the resistance value of our resistor is independent of the frequency, okay? So no matter how much we change the frequency, the resistor is always going to have that exact same resistance, okay? However, the same can't be said for the reactance of our inductor and the reactance of our capacitor. We know that the reactance of the inductor is equal to omega L, and so therefore the reactance of our inductor is directly proportional to omega, and we know that omega is equal to 2 pi f, and so that omega is directly proportional to our frequency, meaning that the reactance of the inductor is directly proportional to our frequency. Similarly, for the reactance of the capacitor, it's equal to 1 all over omega c, so the reactance of the capacitor is inversely proportional to omega, and so therefore the reactance of the capacitor is inversely proportional to the frequency, okay? So as you can see, both the reactance of the inductor and the reactance of the capacitor are affected by the frequency. And so if we look at our phasor diagram, we can see that the reactance of the inductor and the reactance of the capacitor are 180 degrees out of phase. Alright, that just means the vectors are in opposite direction. And so if we were to make XL equal to XC, that means that their magnitudes are obviously the same. Okay, so the magnitudes of the reactances are the exact same. However, because they're facing in opposite directions, If the magnitudes are the same, this means that they're going to perfectly cancel each other out, meaning that our phase diagram collapses, okay, because our XL and our XC are now equal to 0 because they cancelled each other out. And so our phase diagram is just our resistor value. And so as we know, in order to get the total impedance, we must do vector addition on our phasor diagram. However, because there are no other vectors, if we just do vector addition onto nothing, therefore our total impedance is going to equal to the resistance, okay? And as you can see, our total impedance no longer includes any of the reactances, and so this is when our total impedance is at a minimum. And so because our total impedance is at a minimum, this is when our current is at a maximum. And so therefore we can say that resonance occurs in AC circuit when the reactance of our inductor is equal to the reactance of our capacitor. Alright, some few things to note about the circuit now when our circuit is at resonance. When the circuit is at resonance, meaning that the reactances cancel out, this obviously, as we just discussed, means we only have our resistor impeding the current, and so our circuit is now considered purely resistive. And so therefore, if we apply this to this circuit, obviously the voltages of our inductor and the voltages of our capacitor are also going to collapse. Okay? And so therefore, the only voltage left in the circuit is the voltage across the resistor. Okay? Alright, so if we imagine the terminal voltage over here, if the voltages across these two are 0, that means the terminal voltage is going to equal to the voltage across the resistor, okay? And so the voltage across the resistor is our EMF. And so as you can see here, our EMF is now in phase with our current, okay? And that backs up our point earlier when I said that the circuit is now purely resistive. Because if we remember, for a purely resistive AC circuit, our current and our voltage are in phase. Also, just an important note that some people get confused, and I just want to emphasize. The voltages of the inductor and the voltages of the capacitor themselves are not 0, okay? Remember that they still have a voltage, okay? So there is still a VL, and there still is a VC. So the voltage across the inductor and the voltage across the capacitor are still present. It's just when we sum them up, okay? So the vector sum of the voltage across our inductor and the voltage across our capacitor, when we sum those up, that collapses to 0, because they're 180 degrees out of phase. So the voltage itself is still present, it's just when we add them, they equal to 0. And so that is why the supply voltage only appears across the resistor, okay? So in order to get XL equal to XC, we must obviously tune the frequency such that our reactance of our inductor and the reactance of our capacitor are equal. But how do we find that exact frequency? So the way in which we will do that is we will take this equation right here, right? Our XL is equal to XC. We know that our XL is equal to omega L and our XC is equal to 1 all over omega C. And so therefore if we rearrange, we get omega squared LC is equal to 1. We know that our omega is equal to 2 pi f, and so therefore omega squared is equal to 4 pi squared f squared. And so if we sub this into here, we get 4 pi squared f squared LC is equal to 1. Okay, so now we have frequency in the equation. And so now we can rearrange for our frequency, and if we solve for that equation, therefore that gives us the frequency at which this particular circuit is going to resonate at, okay? And so we get our frequency squared is equal to 1 all over 4 pi squared LC. Therefore, our frequency is equal to square root 1 all over 4 pi squared LC. And so therefore we can rewrite this as frequency is equal to the square root of 1 all over the square root of 4 pi squared LC. The square root of 1 is just equal to 1. And so therefore our frequency is equal to 1 all over square root 4 pi squared LC. And we can simplify this further and we get our frequency is equal to 1 all over the square root of 4 pi squared multiplied by the square root of LC. The square root of 4 pi squared is just 2 pi. Okay, so our frequency is equal to 1 all over 2 pi square root LC. And this is the equation that we would use to find the frequency that our particular circuit is going to resonate at. As you can see, it depends on the capacitance and the inductance of the capacitor and the inductor. Okay, and that will be it for resonance in AC. See you.